Okay, welcome to Chapter 2.1, Part B. We're going to pick up exactly where we left off. We're going to start with the topic of using a derivative to find the equation of the tangent line. So far, we've used the derivative to find the slope at a given point, right, to find that instantaneous rate of change of a function. But now we're going to find derivative to find the equation of the tangent line. And I'd like for you to understand that the slope itself, let's just kind of box this whole thing off. There we go. The slope itself is what we've already been finding. We've been finding when we substitute in an x value from a point, we've been finding the slope at that point. But now we're going to use the derivative to find not only the slope of the tangent line, but an equation to use for it. So let's begin by using that limit process with our example. We want to find the derivative of the function y equals 2 over t. And we're also going to find the equation of the tangent line to the graph at 1, 2. Okay. So again, we're going to start by finding the derivative. We're going to use that limit process to do so. So we're going to use another notation. We're going to take the derivative of y with respect to t. I know normally you've seen this as dy over dx. It's really just dy over your independent variable. In this case, that's t. So we're going to take the dy of dt, which means we're going to take the limit as the change in t approaches 0 for our function. So we're going to substitute in 2 over our variable. So we're going to have 2 over, remember our variable is that t plus change in t, minus our original function, which is 2 over t. And on the bottom we have our change in t. We won't make that mistake again of substituting in the wrong values. You guys saw what happened with that today. It was not pretty. Alright, now we take the limit as the change in t approaches 0 after we simplify some things here. What we can say we have is one fraction on top, and here's what I mean. We're going to take the LCD of these two fractions, which would be t outside t plus change in t. And then what we have to do is write that new fraction. Right? We know the bottom of our new fraction is going to be t outside t plus change in t. But then on the top, we're going to multiply each piece by what it didn't have. So this fraction had t plus change in t, but it didn't have t. So we're going to have a 2, and then we're going to have a t. And then up here, we had that negative 2, but we still need to multiply it by what it didn't have. It had the t, but it did not have the t plus change in t. So that's what it's being multiplied by. And we still have change in t at the very bottom of everything. So let's keep going here. I'm going to stop writing the limit thing, but understand that it's, you know what? No, I'm not going to get lazy. Let's write it. Okay. Now when we distribute out, we get negative 2t and negative 2 times the change in t all over t outside t plus change in t all over change in t. Alright, so what we're going to have now, as you can see on the top, our 2 t's cancel. And so just going step by step here, we get negative 2 change in t all over t outside t plus change in t. And now instead of writing divided by change in t, what I'm going to do is I'm going to say times 1 over change in t. You know what? Yeah, let me write that. It's times 1 over change in t. And so essentially what that means is that we have negative 2 change in t, and then we have change in t times t outside t plus change in t. And we can see we have a change in t top and bottom, so we cross those out. And now we have the limit as change in t approaches 0. And we're going to have negative 2 on top, t outside t plus change in t. Now we can substitute in that 0 directly, and we're going to get negative 2 outside t times just the t, because that would go away, and you get t squared. And then we want to find the m, right, the slope at that point at 1, 2. So let's do that on a separate sheet of paper. Right, so far what we've found, the limit as change of t approaches 0 for our function, we've found, for negative 2, I'm just rewriting what we had, for t outside t plus change of t, we found that that equals negative 2 over t squared. So we found that our derivative of y with respect to t equals negative 2 over t squared. So now when we're trying to find the slope at a given point, we want to know the m at 1, 2. We substitute in that 1 to our derivative. So we get negative 2 over 1 squared, which gets us negative 2. Fabulous. So now to get the equation of the tangent line, we have an m and we have a point, so we're going to use our point slope form. We're going to say y minus 2 equals negative 2 outside x minus 1. Y minus 2 equals negative 2x plus 2. Y equals negative 2x plus 4. So here is the equation of the tangent line. And we've answered that question fully, so we're ready to move on. The next example, I do believe that's going to take up some room, so let's talk about the next topic, which is going to be differentiability and continuity. First, however, let's talk about the rule of limits. We know that we can say the following, and I'll explain why in a second. We can say that the limit as x approaches c from the left for our rate of change function, f of x minus f of c all over x minus c, is equal to the limit as x approaches c from the right, or pardon me, I said that wrong, from the right and then from the left, of the same function. And we can say that because of the following thing. Let's talk about this graphically. So say that we had this nice curvy graph. And let's say that we had a point C, and then we had a point X. And we could call this point X, comma, f of x. And we could call this one C, comma, f of c. And what we have going on here, from here to here, we can call this the difference of x minus c. And from here to here, we can call this the difference of f of x minus f of c. Hence, our new and improved, or I guess not really improved, but our new way of looking at the rate of change formula. Change in y over change in x. And we can write a statement next to this to explain why the limits should be the same. As x approaches c, the secant slopes approach the tangent line slope. So again, as we make, let's draw a line through c, comma, f of c, to really get what's going on here. As we make a point from the one we want, c, comma, f of c, and some point out here at x, comma, f of x, and we take the limit of the slopes, right? We take a point out here maybe, and we look closer, and then we look closer, and we look closer, and we look closer, and we look closer, at all those lines. We're taking the limit of those slope lines as they approach the point that we want, right? As this difference gets smaller and smaller, and as this difference gets smaller and smaller. We're interested in the slope as it approaches the point that we're interested in. And the limit should be the same from the left and the right. We should approach the same slope value, making our secant lines in this direction and in this direction. That's all it's saying. It doesn't matter which direction you make your secant lines in, the limits should approach the same value. Okay. Now, let's talk about when f of x is not continuous. Because this example, right, is perfect for when our function is continuous. But what if f of x is not continuous at the point we're interested in at x equals c? That would mean that it's not differentiable. And that's a rule of thumb I'd like you guys to understand. Not continuous, automatically, boom, not differentiable. So let's take, for example, that greatest integer function. Let's take, for example, our f of x equals just the regular old greatest integer of x. Okay. So we would take our graph and let's make sure we have a 1 and a 2. Let's make sure we have a 1 and a 2. Let's label those. Alright, so we have all of our labels. Now let's start to create our function. We know the greatest integer function does this. Right, we just kind of go down one. We'd have the open circles out to the right. Our closed circles happen to the left. And it just goes over and across one every time. Okay. And we can see that our function is discontinuous when x equals 0. And that means that it is not differentiable at x equals 0. Right? If we were to look at the slopes as we approach x equals 0, we get two different directions, right? We can't really make that connection. We can't say, oh, the slope was 0 here and the slope was 0 here, because it's discontinuous and there's that jump there. So we can't say that. Since it's discontinuous at x equals 0, that means it's not differentiable at x equals 0. And end, it makes sense because the limits aren't the same, right? If we were to take the limit from 0, down here we would get -1, and up here we would get 0. We know from the left and the right those are different values, so that would not work out for us. All right, so let's talk about when f of x is continuous, but it would not, you know what, let's start this on a different sheet of paper, hang on. Alright, so new title is that f of x is continuous, but not differentiable. Okay, oops, let's move that over. So, the following case would fit this. If we had the following example, f of x equals absolute value x minus 2 is continuous at x equals 2, but it is not differentiable. And let's figure out why. Let's use that limit definition we just discovered. If we take the limit as x approaches 2 from the left for our f of x minus f of 2 all over x minus 2, we can substitute in some values there, and we can say that this is the limit as x approaches 2, again from the left, of the absolute value of x minus 2, and then we would say minus 0, and then we would say of x minus 2 on the bottom. And we could say this whole thing would be equal to -1. And here, when we take the limit as x approaches 2 from the right, for the same function, so f of x minus f of 2 all over x minus 2, we get the limit as x approaches 2 from the right of the absolute value of x minus 2, oh, that's an absolute value, minus 0, and we have all over x minus 2, and that equals 1. Graphically, this makes sense, and let's explain for a second this absolute value business as well. Why we would get -1 up here is because what we have, let me just use a red pen out here on the side real quick. Whenever we have the absolute value, basically from the left and from the right, what we get, you can see these two are like exactly the same, right? So why do we get two different answers, right? That's so weird. Now, if you actually look at some of the comments I made on your assignments earlier, this is clear, but let's go over why this is clear. If we have the absolute value of x minus 2 over x minus 2, what we actually have are two cases, right? That's how absolute values work. We have the original, right? If we just write x minus 2 over x minus 2, we definitely would have that. And the same thing over the same thing, remember, is just the value of 1. But we would also have the negative case, right? That's how I explained to my Algebra 2 kids. You have an original and you have a negative. So on the top, you would change the sign of the x to become negative x, and you change the sign of the negative 2 to become positive 2, and you have over x minus 2. And this, what we can do is we can factor out a -1 from the top, and we have x minus 2 over x minus 2 again. And we know that x minus 2 over the x minus 2 is just 1, and if we have -1 times 1, that's how we get negative 1. So remember that, I just kind of like draw an arrow down here. The absolute value, the rational expression with an absolute value on top, can be explained this way. You have your positive case and you also have your negative case, and you have 2 answers for that every time. The reason that coming from the left is negative 1 and going from the right is positive 1 can be proven if we look at the graph. And what the graph shows us is this. I know that took a little bit more time to explain, but I felt like that needed to be said because that is kind of counterintuitive just to make that jump. And then we would continue to make our graphs. We had 1, 2, let's go up to 4. Alright, so let's call that 4, let's call that 2. And we would touch here at 2, 0. We would touch here at 0, 2. And we'd have a point here at 4, 2 as well. And then we know that absolute value function just is that perfect V shape. And what we call this is a corner. This function comes to a very sharp corner, and here's what's happening. As we approach that 2, right, the 2 positive, Rm equals 1. And as we approach the 2 from that negative direction, Rm equals negative 1. So if we use that limit definition, our slopes as we approach the point we're interested in, 2, it does not match. The slope over here does not match the slope over here, so we can't take that limit. That limit doesn't exist, so it's not differentiable there. I have one more example of this, which is vertical tangent lines. So again, we call this one a sharp corner. And now let's talk about that vertical tangent line. Alrighty, so if we were to have anything where our function, when we take the limit as x approaches c into that rate of change formula, so f of c minus f of x all over x minus c, and we found that that was either positive infinity, or if we found that this was negative infinity, remember, getting a positive infinity or a negative infinity, that just means the undefined. And undefined, when we're talking about slope, means a vertical line. So that means that graphically, just to kind of picture it, if you ever get positive or negative infinity for your derivative, then what your tangent line looks like is this. Let's call this little S shape our curve. And we're interested maybe in a point right here. And what our tangent line would be doing would be making a perfectly vertical line. That is what would happen. So again, this is something that is continuous. This graph sure is continuous. I never pick up my pen. However, it is not differentiable because the slope right here at the point we're interested in is undefined. And let's see. So yeah, the key point I want you to take away is continuous but not differentiable. And we have 2 cases of that. We have sharp corner. I'm going to write in parentheses absolute value because that's the graph we know makes that shape. And we have vertical tangent line. I'm going to write in parentheses getting positive or negative infinity as our answer. Okay, that's all I have to show you. We'll see you in class tomorrow.